conditions. Yes, please, David.
All right, thank you. So we're going to stay in the Phoenix metro area, but we're going to start to talk a little bit about solutions. And so this particular talk is based on some work that we're doing as part of our Southwest Integrated Field Laboratory, where we're working with community members and local government stakeholders to really try to understand what are the potential solutions, can we deploy them, can we evaluate them, and then ultimately, can we deploy them at scale? And so we are looking at a wide range of solutions, everything from traditional cooled roofs to cool corridors, other green and blue infrastructure, built environment, thermal building characteristics, plans and strategies that local governments can have in terms of implementing solutions, cool paving, and then what I'm going to talk about today in the upper right-hand corner here is the use of an innovative material, a passive radiative cooling material applied to the built environment. So this specific example, the concept is essentially that we use materials that are extremely reflective in the shortwave spectrum, but also highly emissive of their own thermal energy. And in particular, highly emissive in the spectral range between about 8 and 13 microns, where the radiated energy can actually pass through the atmosphere and leave the planet. And so this is the basic concept here. And the project that I'm going to discuss is an actual observational exploration of how these kinds of materials can work in the built environment. Here we have an image of the more typical materials that are used in the built environment in Phoenix in terms of shade structures, whether it's bus shelters or other park ramadas and so forth. And our question is, if we replace those materials or coat them with more highly reflective and highly emissive coatings, what are the thermal benefits? What do we accrue from that? And in fact, what we're going to point out is that there are really three thermal benefits that we can obtain. One is going to be the local benefit to the pedestrian using a shade structure. One is going to be at the neighborhood scale in terms of cooling the airshed. And then the third is going to be the net radiative balance benefit. So here what you see is the traditional surface that is applied to most shelters in Phoenix, has a relatively low solar reflectance and a fairly modest thermal emittance, whereas we are working right now with a product from 3M that is a very highly emissive and highly solar reflective material. We've evaluated this in the lab to demonstrate that, in fact, yes, we are achieving extremely high solar reflectances while simultaneously achieving very high thermal emittance, again, in that 8 to 13 micron range. We've been working on this technology for about 5 years now, initially doing a lot of building energy simulations, asking what are the benefits to buildings in terms of reducing energy load or making the building more thermally resilient to extreme heat, passive survivability of buildings. More recently, just in the last 3 years, we started to actually test this in the urban environment. We've done a lot of side-by-side tests with different kinds of materials on bus shelters, and we have a long-standing test out at our West Campus where we're comparing a conventional bus shelter roof with a passive radiative cooling surface. But what I'm going to talk about today is a larger scale project that we're exploring in South Phoenix in a park where we've actually, with resources from the university and in partnership with the city government, created a park ramada structure, a shade structure. And we established an advanced weather station relatively close to that structure. So this has your standard measurements, temperature, humidity, but also a sonic anemometer to better resolve wind speeds. And then, of course, a pyrgeometer and a pyranometer to measure long wave and short wave radiation downwelling from the sky. Under the ramada itself, we've measured surface temperature and heat flux at multiple locations, as well as we have a pyrgeometer and a pyranometer facing down to look at the reflected and emitted radiation from the surface underneath the shelter. So that's the basic concept. We actually built the ramada back in December, and then in April we put a film coating on it, and immediately it became the coolest surface in the environment in that park. And we initially wanted to do a side-by-side comparison, but really it's cost prohibitive for our budget. So what we did instead was a before-after test case where we used April 17th was the day before we installed the film. And then about 10 days later on April 27th, we had very similar weather conditions. And so we thought that that would be an appropriate before-after comparison. Going forward, all of the figures that you're going to see, the colored lines are going to correspond to orange being the conventional copper-colored surface, blue being the passive cooling surface. And so just to demonstrate that in fact we did have relatively similar weather conditions, on April 27th, we had a very similar incoming solar radiation profile, about 3% more solar radiation than on the 17th. The air temperatures were also quite similar. Again, April 27th being slightly warmer. And the wind speeds were relatively similar, as similar as you might expect for highly variable wind speeds at least, and relatively low. And so based on those observations, we feel that it's actually a somewhat conservative way of evaluating the cool surface because it was actually experiencing slightly more radiation, slightly warmer conditions. So this is our before-after comparison that we're going to look at. So initially, let's just look at the air and surface temperatures above those two surfaces. Again, orange is the conventional surface and blue is the cooling surface. And the air temperatures for the two dates are the dots shown in blue and orange. And as you can see, they're very similar temperatures for the air temperature. But what's really noticeable here, of course, is that the surface temperature for the passive radiative film is almost always below ambient air temperature. A few hours during the day, it exceeds ambient air temperature by maybe a degree or so, whereas the conventional, the old style shelter reached over 50 degrees Celsius. And so as you might expect, that resulted in a better thermal environment for pedestrians using the shelter. So we estimate that over the daytime hours, we had about a 4.5 degrees Celsius reduction in mean radiant temperature for people standing underneath the middle of the cool shelter as compared with the conventional shelter. So that demonstrates, again, the personal benefits to the individuals. Now, we also took our observations in terms of surface temperature, heat fluxes, and wind speeds, and used that in combination with empirical correlations to estimate the total sensible or convective heat flux off both the top and bottom surfaces. So when you have a surface that's cooler than air, the direction of heat transfer is from the air to the surface. When the surface is hotter than air, the heat flow is from the surface to the air. And so what you see is that because the cooling film surface was virtually always lower than air temperature, you have a negative heat flux most of the time. In fact, averaged over the daytime hours, you have about 185 watts per square meter being put into the ambient air shed from the conventional shelter, whereas the cool shelter was actually taking 18 watts per square meter out of the air. So this then, of course, demonstrates the neighborhood scale benefits. And finally, I'd like to talk just briefly about the net radiation balance on that roof surface. So here, the solid lines are the total incoming long-wave plus short-wave radiation incident on the top surface of that shade structure. The dashed lines are the outgoing, so what's either reflected or emitted from the top surface and heading up towards the atmosphere. And again, orange is the conventional surface. And what we see here very, very clearly is that this orange solid line, of course, is substantially higher than the orange dashed line, meaning that the partitioning of that radiation that's incoming is largely staying within the urban environment, whereas for the blue shelter, if you see the dashed line, the outgoing radiation is always larger than the incoming radiation. And so what that means is that you have this net rejection of radiation from the surface upwards towards space. So we can try to make a rough cooling approximation in terms of the global cooling signature, if you will. So what we have here is just a diagram that's suggesting, if you think about the total shortwave radiation incident on the roof and the total long-wave radiation incident on the roof. So this is average over a 24-hour period. And then you ask, well, what fraction of that energy, that radiant energy, is either reflected or emitted and simultaneously makes its way through the atmospheric column and out to space? And what we see is that for the conventional roof, the answer is about a third, about 35% of that incident radiant load actually makes it out to space, whereas for the radiative cooling film, it's more like 58%. So substantial increase in the amount of incident radiation that actually leaves the atmosphere. So I'll just wrap up here with a few quick comments about the findings. So as I said at the beginning, we wanted to demonstrate that this cool surface has the potential to benefit us thermally from three perspectives. And we did find that we had about a 4.5 degrees C mean radiant temperature reduction using this cool film on a shelter. The conventional shelter warmed the air shed on the average of 185 watts per square meter, whereas the cooling film shelter actually cooled the air by an average of 18 watts per square meter. And then finally, the net radiation balance showed that the cooling film actually rejects about 65% more of the incident radiation load away from the surface all the way through the atmospheric column. So as I mentioned earlier, we had initially done some building energy modeling work on this, which is what got us into this topic in the first place. Now what we're interested in doing is exploring the same kind of technology. And there are multiple companies throughout the US and nationally or internationally that are developing, whether they're paint-on coatings, you might have heard Matt Santacourse's talk last night, or film coatings that are becoming cost competitive. And so we're really interested in looking at these applications on buildings where there are a lot of opportunities, but also some challenges, but also on vehicle applications where you might have some substantial benefits because you typically have very little insulation on the rooftop of a vehicle. And then one final note is just that, this is just one potential solution in our arsenal for urban cooling. So I don't want to suggest that this is what we should focus on alone, but this is just one of the many arrows in our quiver, so to speak, to mix metaphors here. So with that, I'll conclude. Thank you.
Thanks, David, for very clear comparison between the conventional roof